Today we're going to be looking at Lesson 6D, Factor and Solving Polynomial Equations. We've already looked at factoring and solving quadratic equations, and we're going to use the same type of rules, but these are going to be higher degrees than just a second degree equation or expression. So there'll be a little bit more involved, but it's going to be the same process. So I brought back up that flow chart that you saw in your lesson 4C, and it might be worth your while just to go back to the video on lesson 4C and watch it one more time, just to get an idea of some other examples. So the first thing we're going to look at is difference of squares. We did difference of squares before. That's where you had like x squared minus 16 is x plus 4 and x minus 4. Or 25 minus x squared is 5 plus x and 5 minus x. The idea of difference of squares doesn't just apply to quadratics. Anything that has an even exponent is a perfect square, so the same rule is going to work for higher polynomials as well. So if I had a to the fourth minus b to the fourth, you just take the square root of the exponents, which involves just cutting them in half. So that would be a squared plus b squared times a squared minus b squared. And then if you can factor those further, you would want to. For example, this one right here is still a difference of squares, so it would actually have another step involved. And so you would keep that a squared plus b squared, because you can't do anything else with that. But the a squared minus b squared factors, as noted up here, as a plus b times a minus b. So when you're doing these higher degree polynomials, you want to make sure that you have completely factored, that whatever method you use, you can't go back and use a different method with any one of the parentheses to break it down a little bit further. So if we look at our first example, we have x to the fourth minus 100. We know this is a difference of squares because x to the fourth can be broken down into x squared times x squared. And then 10 can be broken down, 100 can be broken down into 10 times 10. So if we clean this up, you're going to get x squared plus 10 and x squared minus 10. Now we talked about we want to make sure we can't break this down any further. X squared plus 10 is in its final form. However, x squared minus 10 can factor into x plus the square root of 10 and x minus the square root of 10. And if this was an equation where it was equal to 0, then each one of these factors would be set equal to 0, and you would solve them. Over here at example 2, you want to go back to the idea of the flow chart we talked about. Is there a GCF? Yep, there's a GCF. You're going to bring out that 2n. That's going to leave us a 16 into the fourth minus 1. So yes, we were able to factor by GCF, but if you look at what's left, you still then have a difference of squares. So we have, 2n, and this would be 4n plus 1 and 4n minus 1. And you always want to go back. Can you break 2n down? No. Can you break 4n plus 1 down? No. How about 4n minus 1? No. So once you've broken each individual factor down as far as it can be broken down, you know that you're finished factoring. If it was an equation, it would be at this point that you would solve for n or x. Now, something that you're going to encounter with polynomials that you didn't encounter with quadratics is the sum and difference of cubes. A little bit different because you're working with a cubic function versus a squared function. But when we were doing difference of squares, it only worked for a difference. Sum and difference of cubes works for sums and differences. And the little acronym to help you memorize the pattern we do is SOPs, which is the squared term, the opposite sign, the product of the two terms, it's always plus, and then the other squared term. So SOPs is how we memorize the pattern for sum and difference of cubes. So if you look at this particular problem, the cubic root of this is 3m. And the cubic root of 1 is 1. So those are the numbers we're going to focus on. Your first set of parentheses are exactly what you have up there. It'll be that cubic root, whatever sign is here, and then that cubic root. The second part is where that SOPs comes in. So this first number, this 3m, you're going to square that. So that's going to give us 9m squared. Then whatever sign you used here, you're going to use the opposite. You're going to multiply these two things together. This guy is always a plus, and then you're going to square that last term, which is 1. Okay? So this, 3m plus 1 is completely factored. And then what you're left with here, as long as you get the GCF out ahead of time, is not going to factor. So here, same kind of thing. Is there a GCF? What can go into 16 and 54? So I'm just trying a couple things on my calculator. I think 2 is the largest number, so we're going to factor a 2 out. So then we have 8n cubed minus 27. And then you realize that 8n cubed is a perfect cube. 2n creates that. And 27 is a perfect cube. So we can do a difference of cubes here. So you keep that 2 that you pulled out. 2n minus 3. And then we're going to do the SOPs. So we're going to square the first guy. We're going to do the opposite sign. We're going to do the product of these two terms. Always plus, and the square of the other guy. And so this whole thing would be our factor. So that's sum and difference of cubes. I did it once with a sum, and the second example is a difference. Okay, we talked a little bit about factor by grouping when we looked in Unit 4C at factoring trinomials with leading coefficients. But factor by grouping can actually be used with anything that has 4 terms. So what you do is you just zero in on the first 2 terms. What's your GCF? X squared. And that's going to leave you with x plus 7. And then you're going to zero in on the last 2 terms. And the GCF there is a negative 9. And that's going to leave us with an x plus 7. So what has to happen for this to work is that you have to come up with a common factor there. That guy is going to be one of the factors in your answer. And then those GCFs that you pulled out are going to be the other one. So that's factor by grouping. However, how do you know you're not done? Or you are done? Can you break x plus 7 down any further? No. That's as far as that factor can go. How about x squared minus 9? Well, x squared minus 9 is a difference of squares. So we'll need to break that one down in another step. And then you make sure that each term cannot be factored any further. All right. Look at example 2. GCF. GCF. We're going to do a 4c squared. And that's going to give us a c plus 2 here. And then minus 9. And that's going to give us a c plus 2 here. And these parentheses have to match exactly. So they're both c plus 2. And the other guys are the GCFs, 4c squared minus 9. All right, you can't do anything with c plus 2. But these two can break down into 2c plus 3 and 2c minus 3. And then we're done because nothing else can be broken down any further. Okay, building off of that, I'm going to go back and look at a trinomial, except this time our trinomial isn't a quadratic. So, same kind of thing. We're looking for two numbers that multiply to give me 6, that add together to give me 7. So that's going to be 1 and 6. And then a to the 4th is a squared and a squared. And your signs are going to be plus and plus. And neither one of those can factor any further. Okay, so a squared times a squared is a to the 4th. 6a and 1a squared is 7a squared. And then 1 times 6 is 6. All right. So then we're over here. We know there's a GCF of x, but I'm pretty sure we can pull out a bit more than that. So we're actually going to pull out a 3x. So we have 3x. So then I have 5x to the 4th minus 24 x squared minus 36. So then you want to, this has a leading coefficient, so we're going to multiply the 5 and the 36 together. That gives us 180. Off to the side, we're going to be looking for the pair of numbers that subtract to give us 24. So 1 and 180. That's not going to work. 2 and 90. Nope. 3 and 60. That would give me 57, so no. Let's try 4 and 45. No, that didn't work. 5 and 36. 6 and 30. 6 and 30, they subtract to give me 24. So that's the pair I want to work with. But this is where the factor by grouping is going to come in, just like it did in quadratics. All we're going to do is break that middle term up into a positive 6 x squared and a negative 30 x squared. Okay, because negative 24 is just the same thing as positive 6 and negative 30, so you haven't changed the problem. Now we're going to do our factor by grouping. So we have that 3x out there. And then here you're going to pull out an x squared with a 5x squared plus 6. And then between these two, you're going to pull out a negative 6. And that's going to leave you with a 5x squared plus 6. And when we go to put that together, we have 3x. We have x squared minus 6, those GCFs. And then we have those common factors, 3x squared plus 6. Excuse me, that was 5x squared plus 6. And then if you want to break this down, you can do x plus the square root of 6 times x minus the square root of 6. But I would say most of your problems are going to leave your answer in this format. So a lot of the same methods that we were using earlier, except here we're going to have higher degrees, and it might take more than one method to get it factored completely. So that's lesson 6D. Just take those factors, set them equal to 0, and that's how you'll handle them if the factoring is in an equation form. Thank you.